We are predicting carbon-13 NMR chemical shifts through a machine learning algorithm. So carbon-13 NMR spectroscopy is the main method of determining composition of a molecule, and it works by identifying the chemical shift of each carbon-13 atom in a sample, where the shift of each atom is highly dependent on its neighboring atoms and groups. So we went through a list of molecules and encoded the structure of each molecule as a string using the SMILES format, and then labeled each carbon with its chemical shift. We gathered almost 500 molecules, which included 3,500 carbon centers. Distribution of these chemical shifts is very bimodal, with single bonded sp3 carbons on the lower end and double bonded sp2 carbons on the higher end.
We came up with two naive featureizers to featureize our data. The edge-first featureizer is a sparse dictionary representation of the data that encodes all the chemical bonds, which are edges in the graph, that are within 10 bonds away from the carbon center of interest as features. The vertex-first featureizer emphasizes the type and hybridization of the atoms, which are the vertices, that are within 10 bonds away from the carbon center of interest. It also includes additionally the number of carbons of a particular hybridization state at a certain layer, and it is expected to be more sparse than the edge-first featureizer. To test the featureizers, we first separate the training data into SP2 and SP3 classes, and train two separate random forest regressor models on them. But each regressor model has 1,000 trees and a max depth of 100 in them, with using MSE as their training criterion. We also did cross-validation with 4 iterations using a randomized 1/5 of training data as validation data. As we can see on the right, the model predicts SP3 centers better than SP2 centers in both vertex first and edge first representation, but it does relatively poorly in SP2 carbon centers. So the next step will be to test a more sophisticated feature extraction method that perform better on SP2 centers.
So we came up with a new model for sp2 carbons since they're highly sensitive to substituents due to containing currents. So in chemistry, we don't normally consider individual atoms, but rather groups of atoms called functional groups. And these groups highly affect the current in sp2 carbons. So our model performed slightly worse, probably because very similar functional groups were treated completely separately. But we think a model that combines our previous models will likely improve the performance and stability of the sp2 predictions. And we'll include this in our final paper.